my dear students, now we are going to look at design of 3-bit synchronous up and down counter. So far we have seen 3-bit up counter, 3-bit synchronous down counter. Now we are going to look at how to design up and down at the same time. So what we try to do is we will create an extra control signal which is going to control whether the counter is supposed to act as a up counter or down counter. So rest of the design process will be same. So only thing that we are trying to do is we are adding an extra control signal which is called, let's say, up. So what is this up control is trying to do is it's going to create this up is a control signal. So when up is 0, we are going to do the down counting process. Down counting. Okay. So when up is equals to 1, we will be doing up counting. So what is up counting, what is down counting, we are aware of. Up counting is 3-bit up counting. So 0 0 0, from there it will go to 0 0 1, from there it will go to 0 1 0, what exactly 0 1 0, right? So next is 0 1 1, then 1 0 0, then 1 0 1, then 1 1 0, then 1 1 1, then 0 0 0, then 0 0 1, dash dash dash. It will continue. What about down counting? Down counting is something like this. What is next to 0 0 0 is 1 1 1. What is next? Okay. What is next to 1 1 1 is 1 1 0. What is next to 1 1 0? 1 0 1. What is next to 1 0 1? 1 0 0. What is next to 1 0 1 0 0? 0 1 1. Dash dash dash. Of course, still I can continue, but we are aware of. Okay. So we will, as usual, synchronous counter design will be having 5-6 steps. So in step 1, what we try to do is how many number of flip-flops required. How many number of flip-flops required, either up count or down count. So in step 1, what we try to do is 2 power n should be greater than or equals to capital N. Here it is 3-bit, so it is nothing but modulo 8 counter, n given as mod n. N is capital N is given as 8. 2 power n should be greater than or equals to 8. N equal to 3. Going to satisfy this condition. In step 2, what we try to do is, okay, in step 2, what we try to do is, steps are not listed here as we have seen already. Okay, it's a repetition, so just avoid it. That's all. So in step 2, we choose the number of flip-flops required. The number of which flip-flops to use. Of course, in step 1, we have decided already number of flip-flops. So let's use T flip-flop. Okay. Uh, need not be T. You can go for JK, you can go for SR, you can go for D. But when we are designing a counter, so preferably I take T flip-flop. First priority. So in the step 3, what we try to do is we are trying to draw the state diagram. So state diagram. So how state diagram, what I need to do? I need to do the 2 state diagrams. We have already drawn in 3-bit up counter, 3-bit down counter. Both I need to draw now. When up is equals to 0, then up is equals to 1. And up is equals to 1, up counter. So you have to draw the state diagram of up counter. Right? When up is equals to 0, down counter. So you have to draw the state diagram of down counter. Okay. So what exactly it will be? So up counter 0 0 0 0 0 1 0 1 0, right? So here in the up counter, down counter, we can also fill it up. So let me complete the up counting process. 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So it will move like this. This is state diagram for up counter. Similarly, I draw state diagram for down counter. Okay, so it is look like this. So let's start with say 111. So it will be 110. It will be 101. It will be 100. It will be 011. It will be say 010. Then it will be 001. It will be 000. Right? So from here it will come to this state. From there it will go to this state. From here it will go to this state. This state. Then so 3-bit down counter, 3-bit up counter. This is called 3-bit synchronous. Synchronous. What exactly? Down counter. What about this 3-bit synchronous? Okay, synchronous up counter. Done, right? So 3-bit synchronous up counter, 3-bit synchronous down counter. Both we have seen. So for this, what we try to do is we try to develop an excitation table. What is excitation table? Excitation table. Excitation table for what? 3-bit synchronous. Synchronous. Okay. Up and down counter. So this is what exactly we need to develop. What exactly this step? This is step 4. So that we will see now. So what will be there in this step 4 is we will be looking at the present state. Present state. Then we will be looking at the next state. What exactly we need it. Okay. Present state and next state. So next state we try to draw. Look at next state. Next state. Then we are going to look at flip-flop inputs. What exactly the flip-flop inputs such that this present state to this next state the set of flip-flops going to move. So what flip-flop inputs are required for the current in present state to current next state what we are looking for. So in addition to that, what we try to do is along with the present state, I'll introduce a extra control signal up. When up is 0, we will be doing down counting. When up is 1, we will be doing, so what we are doing is up is equal to 0, down. When up is equal to 1, up counting. Okay. So that is what exactly extra thing that is going to come, rest all are same. So what is going to have is this excitation table. Excitation table is going to contain up counter excitation table plus down counter excitation table with an extra control signal up when up is 0, down counting when up is 1, up counting. That's all. So in the present state, let's have I have 3 flip-flops. Let's say QA, QB, QC. Okay. When up is equals to 0, when up is 0, during this process, when up is 0, for 000 is going to next state as okay 111. For 001 it is going to 000. That means it is counting down. Okay. So when 010 it is 001. For 2 to 1 it is going, 3 to 2 it is going, 4 to 3 it is going. Likewise it will be there up to 0 to 7 is your down counter. Let's say this is QA plus 1, QB plus 1, then QC plus 1. Let us use the flip-flops TA, TB and TC. Once this is clear, then when up is equals to 1, this is what exactly the case. Up is equals to. Now look at that present state to next state. Present state to next state is when 000 is a present state. Let's say this is the 000 is a present state. So now the next state that we are going to 001. That means counting up. For 1 it is 2, for 2 it is 3, for 3 it is 4, for 4 it is 5. Likewise for 7 it is next state is 0. So this is up counting, down counting is available. and extra input signal up is there. So when you consider up is an input signal, then the sequence serial numbers, in order to get the min terms, okay, what I gave is the serial number. So it is going from 0 because there are 4 inputs now along with the present state and present input, we call it as present input, PI. Present input of course is up. So this input, because of that we are going to get 0 to 15 cases, totally 16 cases. But if I take individually any up counter or down counter, only 7 cases. So now because the inputs are 4, I need to use 4 variable KMF. In 3 bit up counter or down counter, we have used just 3 input KMF. Now we need to use 4 input KMF. That's all. Now what do we need to do? We need to find it out. That what is the TA value for QA plus 1. Compare 0 1. We know already the excitation table for T flip flop. Present state is Qn, next state is Qn plus 1, then the input T. For 0 0 input is 0, for 0 1 input is 1, for 1 0 input is 1, and 1 1 input is 0. What is the meaning of this is when they are different we need to give 1 input. That means right now it is 0. If you want to get next also 0, what is next also 0 means after application of the clock. This is good, right? So what I try to do is I try to write the TA values. Now if you compare this 1 0 0 1, as we have seen already in up counter or down counter, it is always changing. So the input is 1 1 1 1 1 for down counter. Even for the up counter, if it is 0, it is 1. For 1, it is 0. So it is continuously changing. So for all the cases, it is 1 1 1 1 1 and 1. Next you try to compare QB and QB plus 1. 0 1 0 0. So 0 1 means it is 1, 0 and 0, comparing these two. So for 0 0, what exactly is 0? Next 1 0 1 0, so 1. Next 1 1 0. Next 0 1 1. Next 0 0 0 1 0 1 1 1 0. Okay. Next what I need to do? Next I need to look for the rest of the numbers. For 0 0 0, for 0 1 1, for 1 1 0, 1 0 1 0 0 0 0 1 1 1 1 0 1 0 1. Okay. Not next. Next we need to look at QC plus 1 with QC. So this is 0, this is 1, it is 1. Now if you look at this, rest 3 are zeros here and these 3 are zeros. So I can put 3 zeros consecutively. Right. Next, if I compare this 1 with this 0, so it is 1. For this 3 ones here and here also 3 ones, so 0 0 0. Next, if you compare this, here 3 zeros, here 3 zeros, so 0 0 0, right? 3 zeros done. Next, this is also 0 and whereas this is 1, right? So it is 1. Next, if you look at these 3 are ones and these 3 are ones. Okay, this is 0 1, that is already covered. 1 second. What I try to do is this 3 should be compared with the QC plus 1, this 3. So this 3 is 0 0 0. When I compare this one with this 0, so it is different. So now I got the values of what exactly? TA, TB, TC. Now use the values of TA in the KM. So it is what exactly it is? It is 1 for always. So 1 1 1 1 1 1 1 1 1 1 1 1 1 1, all 16 ones. Combine them. what you are going to get is, this is for TA. We are going to expression for TA as well. Next, what exactly I need is TB. If you want TB, just look at the things. Okay, write the expression for TB. So if you look at the TB, what are the min terms that are there? For TB, I can write TB as sigma m. Okay, what are the min terms that we have? For TB, it is 0, then it is 2, it is 2, 0, 2, 4, and 6. Okay, and also we have further, what are they? Is what are they that we try to write here? Continuation. After 6, if you look at what exactly this value turns out to be 9. So 9, 11, 9, 11, 13, and 15. This is 13 and this is 15. So total. So this is what exactly TP. So 0 to 46, 9, 11, 13, 15. 0 to 46. So TB is nothing but sigma m 0 to 46, 9, 11, 13, 15. We know the serial numbers, of course, we will enter them. So this is 0, of course, 1, 2, 3, 4, 5, quickly, just this is 7, this is 6, this is 8, this is 9, this is 11, this is 10. Okay, by this time you should be very much comfortable with working with KMAP. So 15 and 14, right? So 0 to 4, 6, 0 to 4, 6, 9, 11, 9, 11, then 13 and 15, 13 and 15. So I can combine this 4 and I can combine this 2 with this 2. So now I will get the expression for TB as what exactly? The expression for TB is, if I look for this, of course I will get it TB. The TB values turns out to be, here I am going to get it as bar, then it is QA bar, okay, QA bar, okay, plus what I got is, what is here is up, what is here is QA. So up QA. Similarly, we need to look at QC bar, QC. So for TC. So what I need to do is, for TC, I need to write the expression for TC, sigma m. What exactly those values? I need to look at it here from the table, and we will try to use it. So it is for TB express, TC expression, TB expression we have already seen, sigma m. It is 1 for 0. For 0 it is 1, right? And it is 1 for what exactly? 1 for 4, 0, 4. And is there any other ones? No. So it is 1 for, see this one, as for 11, and 1 for 15. So 11, 15. So 0, 4, 11, 15. So we will use those values, 0, 4, 0, 4, 11, 15. So that I will get the expression for this. So 0 is this, 4 is this. Okay. Where is 11? So 8, 9, 10, 11, and 15. So this 2 and this 2. What is the expression for TC? TC turns out to be QA bar, QB bar, up, UP up bar, because this is 0. Okay, up is MSB, right? So up bar, then what exactly here it is? QB bar, QA bar. Plus, if I see in this up, UP up, okay, QA, QB, and QA. Okay. So with this, what I try to do is, I'll take 3 flip-flops and try to draw the diagram. So TA is always 1. There is no TD. TB is up bar Q. What exactly we got it in TB? QA bar up plus QA plus up QA. Whereas TC is up bar QB bar QA bar plus, okay, up QB QA. Okay. So if you observe these expressions, there is certain things are there. Okay. So if you leave about up and up bar, if you refer to the up counter and down counter, for a down counter, what we got is TA is equals to 1, TB is equals to, okay, what exactly? QA bar, okay, QA bar you are going to get. Just check it out. Up bar, QA bar, right? So this QA bar. For TC, it is QB bar and a QA bar. This is for down counter individually. For up counter, what we got? TA is equals to 1, TB is equals to QA, TC is equals to QB, QA. Okay, we got the same. The only thing is just we have added in the expressions. Okay, so down when up bar is there, up when up is equals to 1. So the same thing is added with it, these terms, and it is being there. Of course, TA case is always 1, it is always 1. Okay. Now you can understand how up expressions are, how down expressions are, and how up down expression is. This is important thing one has to understand. Once this is being done, rest is draw the circuit diagram. So how to draw the circuit diagram? Very simple. I'll take first one flip flop, then I'll give a gap, then I'll take another flip flop, then another flip. Let's say this is flip flop A, this is flip flop. What is flip flop A? Flip flop A is LSB. So better we write here. So flip flop A is here. Next B is here. Next C is here. It's a T flip. So it will be having QC, QC bar, QB, QB bar, QA, QA bar. QA bar available, QA available, QB available, QB bar available, QC available, QC bar available. Right? Once this is being done, now I will take the input TA. This is TA. Is it TA? No, it's TC. This is TC. We'll be having TB. We'll be having TA. What we know is for TA, it is always 1. So I'll connect it to 1. What is TB is TB we are going to connect with a processing. So what we try to do is I use a 2 AND gates. For 2 AND gates, what I try to do is one of the input is up bar, QA bar, up bar, QA bar. The another for that up QA. From these two, I'll give it to OR gate. I'll get my output done. Whatever is there, I'll connect it to T. Similarly for TC, what I try to do is I try to take 3 input AND gates, 2 AND gates. Okay. So up bar, QB bar, QA bar, up bar, QB bar, QA bar, up, this is up, QA, QB. These two I am going to OR it. Once ORing is done, that I'll connect it to. Okay. So this is how one can design up down counter. Is the design complete? Yes, of course, but we need to have a common clock for all the flip flops. So common clock, synchronous counter, common clock input. This is clock input. Okay. So here you will get Q bar, QB bar. If you want QB bar from here, QA bar from here, QC bar from here. Of course, we don't require QC bar. PA bar, QB bar. I can show explicit connections, but if I take that, it will be complex. So directly I have written QB bar, QA bar. Actually, if I say QB bar here, this should be connected to here for this. Okay, done.